To size conductors for continuous loads, a simplified method can be used that involves 3 steps. Firstly, determine the overcurrent protective device, also known as the oct. This is done by multiplying the continuous load by 125% and rounding up to the next standard size oct. Secondly, determine the conductor size from Table 310.16 in the National Electrical Code. Find the column in Table 310.16 that corresponds to the temperature rating of the terminals or circuit breaker. Multiply the continuous load by 125%. Then locate the value in the selected column that is equal to or greater than the calculated value. Round up to the next standard conductor size. Thirdly, adjust for correction and adjustment factors if they are applicable. If no adjustment or correction factors are present, this step can be skipped. To adjust for these factors, first find the next low standard oct that is smaller than the value determined in step 1. Add 1 amp to the reduced oct value. Divide the reduced oct value by the product of the correction factor and the adjustment factor. Refer to the selected temperature column in Table 310.16 and find the conductor size that corresponds to this value. Round up to the next standard conductor size. Some additional notes to consider include temperature ratings. Temperature ratings should be considered for both the conductor and the connected equipment. This is important because the ampacity of a conductor is affected by its temperature rating and the temperature rating of the terminals to which it is connected. It is generally required to use the lowest temperature rating of either the conductor or the termination point when determining the allowable ampacity. Another consideration is parallel conductors. When multiple conductors are used in parallel, the total continuous load should be used to calculate the required conductor size. Each parallel conductor must be of the same length, conductor material, cross-sectional area, have the same insulation type, and be terminated in the same manner. This ensures that the load is evenly distributed among the parallel conductors. It is also important to ensure that the overcurrent protection device protects all conductors in the circuit. Consider an example where a continuous load is 50 amps and the terminals are rated for 75 degrees Celsius. Firstly, determine the oct. 50 amps multiplied by 125% equals 62.5 amps. Round up to the next standard size oct, which is 70 amps. Secondly, determine the conductor size from Table 310.16. In the 75 degrees Celsius column, find a conductor that is rated for at least 62.5 amps. According to Table 310.16, a number 6 American wire gauge copper conductor with THHN insulation is rated for 65 amps in the 75 degrees Celsius column. Thirdly, check for any adjustment or correction factors. If the conductors are installed in an area with an ambient temperature higher than 30 degrees Celsius, a temperature correction factor will need to be applied. For example, if the ambient temperature is 40 degrees Celsius, the correction factor for THHN conductors is 0.88. If there are more than 3 current-carrying conductors in a raceway or cable, an adjustment factor will also need to be applied. For example, if there are 4 to 6 current-carrying conductors, the adjustment factor is 0.80. Multiply the two factors together, which is 0.88 multiplied by 0.80, which equals 0.704. Find the next lower standard oct that is smaller than the step 1 value. The standard size below 70 amps is 60 amps. Add 1 amp to the reduced oct value. The result is 61 amps. Divide the reduced oct value by the product of the correction factor and adjustment factor. 61 amps divided by 0.704 equals 86.65 amps. Refer to the 75 degrees Celsius column in Table 310.16 and find the conductor size that corresponds to this value. According to Table 310.16, number 3 American wire gauge copper conductor with THHN insulation is rated for 85 amps, so the next largest standard size is a number 2 American wire gauge conductor with an ampacity of 95 amps in the 75 degrees Celsius column. Using this simplified method, electricians can accurately size conductors for continuous loads, ensuring safe and compliant electrical installations. Always refer to the latest edition of the National Electrical Code and local codes for specific requirements and guidance. The key to accurately sizing conductors for continuous loads lies in understanding and correctly applying the relevant sections of the National Electrical Code, particularly Article 210, branch circuits, Article 215, feeders, and Article 310, conductors for general wiring. Let's delve deeper into some key aspects of conductor sizing for continuous loads. Firstly, ampacity correction and adjustment factors. The National Electrical Code requires that the ampacity of conductors be adjusted or corrected for certain conditions, such as high ambient temperatures or the presence of multiple current-carrying conductors in a raceway or cable. Ampacity correction factors are applied when conductors are installed in environments with ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. These factors reduce the allowable ampacity of the conductor to prevent overheating. Ampacity adjustment factors are applied when there are more than 3 current-carrying conductors in a raceway, cable, or earth. These factors also reduce the allowable ampacity of the conductors to prevent overheating, as the heat generated by multiple conductors can raise the overall temperature within the enclosure. Secondly, temperature ratings of terminations. Temperature rating of the terminations at both ends of a conductor is a critical factor in determining the allowable ampacity of the conductor. The National Electrical Code specifies that conductors must be selected and installed so that the temperature rating of the terminations is not exceeded. This means that the conductor must be sized based on the lowest temperature rating of any termination in the circuit, including terminals on circuit breakers, switches, and equipment. For example, if a conductor is connected to a circuit breaker with a 75 degrees Celsius termination rating, the conductor must be sized based on the 75 degrees Celsius ampacity, even if the conductor itself is rated for 90 degrees Celsius. Thirdly, voltage drop considerations. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends that voltage drop on branch circuits should not exceed 3%, and voltage drop on feeders should not exceed 5%. To minimize voltage drop, conductors may need to be sized larger than required for ampacity alone. The formula for calculating voltage drop is voltage drop equals current multiplied by impedance. The impedance of a conductor depends on its length, cross-sectional area, and material. Larger conductors have lower impedance and therefore result in less voltage drop. Fourthly, conductor types and insulation. The type of conductor and its insulation also play a role in determining its ampacity. The National Electrical Code recognizes various types of conductors, each with different insulation materials and temperature ratings. Some common types of conductors include THHN, THWN, and XHHW. THHN conductors have a thermoplastic high heat-resistant nylon jacket insulation and are rated for 90 degrees Celsius in dry locations. THWN conductors have a thermoplastic high water-resistant nylon jacket insulation and are rated for 75 degrees Celsius in wet locations. XHHW conductors have a cross-linked polyethylene insulation and are rated for 90 degrees Celsius in dry locations and 75 degrees Celsius in wet locations. The insulation type affects the conductor's ability to withstand heat and moisture, which in turn affects its ampacity. Fifthly, continuous versus non-continuous loads. The National Electrical Code defines a continuous load as a load that operates for 3 hours or more at a time. For continuous loads, conductors must be sized to carry at least 125% of the continuous load current. This is to account for the fact that continuous loads generate more heat than non-continuous loads. Non-continuous loads are loads that operate for less than 3 hours at a time. For non-continuous loads, conductors can be sized to carry 100% of the load current. Sixthly, parallel conductors. The National Electrical Code permits the use of parallel conductors in certain situations, such as when the required ampacity exceeds the ampacity of the largest available conductor size. When conductors are installed in parallel, they must be of the same length, conductor material, cross-sectional area, insulation type, and be terminated in the same manner. The overcurrent protection device must also be sized to protect all of the parallel conductors. The ampacity of the parallel conductors is the sum of the ampacities of the individual conductors. Seventhly, the rating for conduit fill. The National Electrical Code specifies the maximum number of conductors that can be installed in a conduit or raceway. When the number of conductors exceeds the maximum allowed, the ampacity of the conductors must be derated. This is to prevent overheating due to the close proximity of the conductors. The derating factors depend on the number of conductors in the conduit and the type of installation. Eighthly, grounding and bonding conductors. Grounding and bonding conductors are used to provide a path for fault current to return to the source, which helps to protect against electric shock and fire hazards. The National Electrical Code specifies the minimum size of grounding and bonding conductors based on the size of the overcurrent protection device. Grounding and bonding conductors must be properly installed and connected to ensure effective grounding and bonding. Ninthly, overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are used to protect conductors from overloads and short circuits. The National Electrical Code specifies the maximum size of the overcurrent protection device based on the ampacity of the conductor. The overcurrent protection device must be sized to protect the conductor without causing nuisance tripping. Tenthly, documentation and labeling. It is important to properly document and label all electrical installations, including conductor sizes, ampacities, and overcurrent protection device ratings. This helps to ensure that the electrical system is safe and easy to maintain. Labels should be placed on conductors, conduits, and equipment to identify their function and characteristics. By carefully considering all of these factors, electricians can accurately size conductors for continuous loads and ensure safe and reliable electrical installations. Remember to always consult the latest edition of the National Electrical Code and local codes for specific requirements and guidance.